enough. And what we'll try to talk about quickly is sort of what are some of the issues that arise in photocatalysis that differs from traditional heterogeneous catalysis, and talk about that in terms of the band gap and band energy positions of the materials. Talk a little bit, although there's been a lot less work here, about how the kinds of experiments people are trying to do to develop surface reaction mechanisms for photocatalysts, which isn't easy. Then talk about some of the types of materials and maybe system designs that people are using for the photoelectrocatalytic conversions. And again, I'll maybe make the disclaimer now that we're definitely not going to talk about all of them, as people are talking about many different geometries, but we'll try to take a look at a couple of representative ones. And then talk about some of the innovations that are needed for further progress in this area. Okay, and there's a significant amount of work kind of both in, obviously there's a significant amount of work in water splitting, but there's been a lot of work in the catalysis community in using photocatalysts to sort of go in the opposite direction of destroying organic contaminants. So for example, a photocatalyst like titania is often used in exterior white wall paints because it has a self-cleaning function that when sunlight shines on it and it's in the atmosphere, it will actually react carbonaceous material with oxygen pretty efficiently to make CO2 and water. So that you can get this self-cleaning action. And so basically, whenever you want to do this reaction, there are a couple of options. You could use a catalyst like platinum in a high-temperature reactor. This compound, you wouldn't have to burn too high a temperature, but several hundred degrees C, say, in order to really get this reaction to go. But the advantage of photocatalysis for these kinds of applications is that you can do it at room temperature. You just need exposure to light. And titania is probably the most studied photocatalyst for this reaction. Titania is a relatively wide band gap material, and so its band gap is a little bit larger than you would like for visible light applications. That mainly is in the ultraviolet range of the spectrum where you get the promotions, and we'll talk about all that in a minute. But it's a very good catalyst for these kinds of applications, especially if you put in a little bit of platinum, as we'll talk about, or some other metals we'll talk about in a minute. Okay, so what's happening in a general photocatalytic reaction? And when we get to water splitting, we'll put up a very similar kind of diagram here. It will just be happening in the reverse direction. So this is let's say a titania nanoparticle, and we have and we'll start with the surface reactions. We have a couple of reactions going on. So if we're trying to decompose these volatile organic species, then we can reduce oxygen with electrons that are available on the surface. And this O2 negative, maybe this isn't the best diagram, it doesn't really come off the surface. So it stays on the surface and it subsequently dissociates. And this is kind of the key first step in the reaction. And the key first step on the other end is that a hole or an electron vacancy can react with the carbonaceous material, right, to form a positively charged surface-absorbed intermediate, and then this subsequently can decompose on the titania. And of course, where you get the electrons and holes is important, right, and that can occur. That occurs basically through radiation of ultraviolet light, usually in the case of titania. And that radiation can cause you to form electron-hole pairs that you excite the electron across the band gap into the conduction band when you've chosen the appropriate minimum energy for the excitation. And we'll talk about how the position of those energy bands is actually critical in applications like water splitting. All right, so these kinds of catalysts are used commercially, which is one reason why I wanted to bring them up. The photoelectrochemical water splitting, those devices are still pretty expensive, but these sorts of photocatalytic applications are actually used commercially. You can buy units like this, where you basically have a reactor with some UV lights surrounding it, and then you can flow in organic and air or oxygen and make CO2 and water, basically. So I'll show you a couple of experiments with using this kind of setup. And so one interesting thing that we see that is sort of an echo of electrocatalysis is that the presence of a solvent really affects the way the reaction proceeds. Right? And so this is something that obviously is going to be important when you have a photoelectrochemical cell for water splitting, that you're going to have solvent there, you're going to have water. And you're going to be wanting to dissociate that water. And water really affects the way that these organic compounds, for example, react. And so this is an experiment where we're feeding formic acid, which is this compound, and then we switch the lights on in the reactor. There's no reaction initially. We switch the lights on, there's a dramatic increase in rate, and then it slowly decays. This is a transient experiment where actually we're not continuously feeding formic acid, I misspoke. So formic acid was initially put down on the surface and we're watching it react away. All right, so it starts reacting away, follows this exponential decay, and then when we inject water, the rate of reaction actually goes up dramatically. It goes up by about an order of magnitude. And so the water really is coordinating with the intermediates on the surface to change the way in which they react. And this is going to be important in a lot of the photoelectrocatalytic processes, just as it's important in the electrochemistry that we saw in the last session. Okay, it's pretty well understood now how this is happening in the case of formic acid, that when water comes in, it forms, again, hydrogen bonds to the adsorbed intermediate and allows for a more easy dissociation of the first OH bond. Right, so water is very good for shuttling protons around, which is important in a lot of these reactions. The other thing that the water does that will get us into kind of the right area for talking about water splitting, right, is that it affects the relative positions of the valence band and the conduction band of the material. So again, what we need to do is we have in these semiconducting kind of materials, right, what we need to do is promote an electron from the top of the valence band into the conduction band, and then we can do our chemistry with our holes that are here at the top of the valence band and our electrons that are at the top of the conduction band. All right, but remember, just as in the case of water splitting, right, when we have these electrons and holes, and we're going to be doing two half reactions, one that involves the oxygen up here actually, and one that involves the volatile organic, right, there has to be a minimum charge separation in order for the reaction to go the direction that we want, or a minimum energy separation, excuse me. All right, so in the case of water splitting, that's going to be that this needs to be at least 1.23 volts. All right, but really, it's going to have to be greater than that in order to do the water splitting that we want. Okay, and it's going to have to be greater than that in order to do this reaction. All right, that we're going to need more energy than the minimum in order to do the reaction. And so the position of these bands are important. And it's not just the gap that's important. So we have reactions, we have the two half reactions, and the oxygen reduction reaction has to occur below the conduction band. And the more below the conduction band it is, the higher the overpotential, and so the faster the reaction will go. Right? Just as in an electrochemical reaction. So you're increasing the driving force the further below the conduction band you are. And conversely, the further above the valence band position you are, the faster the reaction will go, the higher the potential on that end. So the greater the driving force for the transfer of electrons to holes. Okay, and so because of that, although wide band gap materials are disadvantageous from the perspective of it takes a lot of energy to promote an electron from the valence band into the conduction band, the advantage of wide band gap materials is that they tend to have a greater driving force for the reaction to occur. And so we'll take a look explicitly at this trade-off for water splitting, but it'll come up actually here, right, that increasing reactivity corresponds with a greater distance between the valence band and then the fixed potentials that will lie in here for the oxidation and reduction reactions. Okay, so this is the band gap for TiO2, and we're tracking the electron density of the surface atoms to see where they are, because you need the difference to exist between the potential for the reaction and the energy of the electrons and holes of these atoms. Okay, and so what we see that is pretty typical is that when you have intermediates on your surface, so you have formic acid and here's an adsorbed H atom on the surface, and this is just one example. that you tend to get a shifting of the bands that disfavors one of the reactions. So the bands tend to shift in the same direction. All right, and so what's happening in this case is because we're shifting the conduction band to the left, and we have a fixed potential for our oxygen reduction that's here, that means we're decreasing the driving force to get our reaction to go for the oxygen reduction. All right, so that's going to tend to slow down the rate of reaction. And the nice thing about adding water, one of the things that it does, is that it weakens the interactions of the adsorbates with the surface, okay, and therefore shifts the bands back to their original position so that you have enough of a driving force on both ends in order to do the reaction. And we'll look at this maybe with some more specific numbers in just a minute. Let's skip that part. One interesting thing that you often see that I just thought I would point out, this is with a titania surface, during these reactions with volatile organics, is that you actually, if you just take a sheet of titania, or a single crystal of titania, and put water on it before you clean it, then you actually see the water bead up. And then if you expose that to light, then the water actually wets the surface. And then you can wait for a while in the dark, and the water will bead up again. Okay, and so what's happening here is that you have an organic that's absorbed on your surface that the water doesn't want to interact with, because this is a hydrophobic type adsorbate. And then as you turn on the reaction by turning on the UV light, you start to react the oxygen with the volatile organic, and the water ends up wetting the surface of the catalyst. And so this is just sort of a cool picture that goes along with these kinds of reaction chemistries. Okay, so how do we experimentally study these kinds of photocatalytic reactions? And basically, this has been done a lot less, but basically you use the same sorts of techniques that I talked about yesterday that you can use, for example, a mass spectrometer to look at volatile reaction products. But you also have to incorporate in there the ability to shine light on your sample. And this shows a setup where somebody's done that, but it's actually relatively rare that people will go through the trouble to do that for all of their analytical techniques. That coming up with a geometry that works, that you can both see the surface spectroscopically and shine light on it. It's not that it's not doable, but not many people have taken the trouble to modify their systems to do that. So these sorts of studies are still relatively rare, although you see some of the kinds of studies like this. And so the study that I'll talk about very briefly has to do with one of the steps in water oxidation. So you want to take water, and one of the products that you want to make from it is O2. So you want to bulk both O2 and H2 during the reaction of water. And so to probe this, or to look at one step of this, one step is that you need the O2 to come off of the surface after it's made. And as we've seen, when the O2 is on the surface, it has a negative charge associated with it. And so you need to transmit a hole to the O2 to get it to desorb. Okay? And so this has been studied using this kind of setup where they can shine light on an O2 pre-dose surface in order to see the dependence of oxygen desorption with the light. Okay, and so what you see, not surprisingly, is that O2 doesn't really desorb. This is conducted at low temperature, but O2 doesn't really desorb until you get up to a photon energy that's above the titania band gap, and then it starts to take off, and then you get an increase. And another thing that you see is that as you increase the flux of photons to the surface, that you initially have this, you have a half-order dependence here on the, I guess you're plotting the flux to the 1/2 versus the yield of oxygen, that it actually follows a linear trend. And this is a little bit of a complicated story why the slope changes, so we won't focus on that so much. But you get a linear trend to the half-order. And don't want to go through the details of this model, but what this indicates is that actually what's limiting the reaction is not the reaction rate, but in fact electron-hole recombination. Right? And so one of the real issues in designing photocatalysts and the materials onto which you deposit photocatalysts on the surface is trying to design the materials in such a way that you can get a lot of the reaction and not a lot of the electron and holes just recombine them before they ever are able to participate in the reaction. So there have been a number of studies of reactions that are conducted not in the light that involve oxygen and water and hydrogen in order to try to understand some of the elementary steps that are taking place during these reactions, at least the way they take place in the absence of light. And so one interesting thing that people have observed is in titania and some of these other oxide materials, that it's a mistake to think about them as being a fixed matrix of a material. That actually the titanium and oxygen atoms are very mobile and can move around inside the material to participate in reactions. So for example, in the dissociation of oxygen on titania, so this is an O2 negative that's absorbed, using both STM and density functional theory, this group has seen that to do this dissociation, titanium actually migrates through interstitial spaces up in the bulk up to the surface. And this extra titanium atom gets added to the surface, and then that's the titanium atom that promotes oxygen dissociation. So you can see some very complex mechanisms here. And then again, if we're looking at water splitting, you would potentially see just the reverse, that the dissociated oxygen that you wanted to ultimately form O2 might need to interact with this surface titania and then lose that interaction in order to dissolve as O2. Okay, I think maybe I'll skip this. This just again points to the complexity of some of these reactions. Again, looking at water splitting and oxygen reduction in the dark. So I think I'll skip that and get directly at some of the water splitting materials. Okay, so if we're going to do water splitting, now we'll look specifically at the reactions that we need to do. So one of the reactions that we need, so we want to take overall, we want to take water as our reactant, and we want to make hydrogen and oxygen. And in order to make the hydrogen, what we'll really be doing, although in a lot of diagrams you see it show up as water, typically you'll dissociate a water and you'll make protons. And so one of the things you'll be doing is reacting those protons with electrons to make hydrogen. So you have solvated protons going to form hydrogen by reacting with electrons that you're producing photochemically. All right, then the holes will come and react with the water in order to make oxygen. Right? And the energy difference between the electrons at the bottom of the conduction band and the holes at the top of the valence band is going to need to be at least 1.23 volts in order to do this reaction under neutral pH conditions. Okay, this shows the case for a titanium material. We have a lot more than 1.23 volts. I think I have a slide coming up that shows exactly where the position of the bands are with respect to the potentials for the water reduction and water oxidation chemistries. But again, you need holes, that there's some driving force, that the water to oxygen reaction is at a potential that's above the top of the valence band. And for the reaction where you produce hydrogen, you're going to need electrons that will want to flow from the conduction band to a potential that's somewhere inside the band gap. And this actually shows, I guess, a two-catalyst device where you get electrons flowing to do the reaction over here at this electrocatalyst. It's not actually even a photocatalyst. Okay, and maybe it's useful to point out here that there are a number of geometries that are being investigated for photoelectrocatalytic water splitting. Okay, and one of those involves just that you have a lot of these catalyst particles that are floating around in a bath of water, and you're going to shine light on them. Okay, and so that would be this kind of picture where the same particle is doing both the oxidation and reduction chemistry. Right? The disadvantage of this approach typically is that you form the oxygen, for example, but then it can migrate to another site and you have hydrogen around, and it can undergo an undesirable reaction to reproduce water. Right, and so another scheme that's often used is that you actually separate out the two reactions. So you have the water going to form oxygen, on this semiconductor device, and then titania actually isn't a very good catalyst for this reaction anyway, and other semiconductors tend to not be a very good catalyst for this reaction. And so you would just use an electrocatalyst that really isn't a photoactive material on this side, where you're just using the driving force for this reaction to make electrons flow through here to do the standard hydrogen evolution reaction, so making hydrogen from protons. Okay, so I think the only reason I'm putting this up is to show sort of the same picture, right, that you need to have this kind of process taking place. Typically, these kinds of oxide materials are doped with at least a small amount of platinum or some other metal to do the formation of hydrogen, so to make hydrogen from protons, because oxide materials are not very good at that reaction. They're not very good at producing hydrogen. Right, so you typically need some precious metal. Okay, so I mentioned the importance of choosing an appropriate material so that you have the band gap positioned appropriately. This looks at a number of common semiconductor materials and looks at their the position of the top of the conduction band, or excuse me, the bottom of the conduction band and the top of the valence band. All right, and what we see is that, so here is our reaction for the conversion of protons to hydrogen, and here is our reaction for the conversion of water to oxygen, or vice versa. All right, and we have a 1.23 volt separation here, you can see. Okay, and what we typically see, or what we see here is that you need, first of all, a band gap that is at least 1.23 volts, but the position of the bands also matters. So for example, cadmium selenide can't be used for electrochemical reactions that involve the conversion of oxygen to water. Okay? Something like titania, for example, that's probably the most studied material, all right, its band gap is big, so its band gap is certainly big enough, but it just barely, the bottom of the conduction band is just barely above the proton-hydrogen potential. All right, so there's not a very strong driving force for this reaction, and so it's not a very good catalyst for this reaction. All right, but you have actually more than enough driving force with titanium to do the oxygen to water reaction. Okay, and so what you would typically want to choose would be, hopefully, a material like cadmium sulfide here, all right, that sort of straddles the potentials of the two reactions you want to do relatively evenly, with a not huge but significant driving force to do each of the reactions. Any questions about that, about how the band positions work? Okay, so of course, so titania is a simple material that there have been a lot of fundamental studies of, but there are lots of very exotic oxides and other types of materials that people are looking at as the photoactive material. And next week we'll talk about organic materials that are used as the photoactive material. And so when you get into these complicated structures that may involve an inhomogeneous type of particle, so we'll take a look at one example here that involves a nickel oxide that's located on the surface with this complex oxide that's constituting the bulk of the material. All right, then actually paying attention to the position of the bands becomes a little bit more complicated, as we'll see on the next slide. And so what I want to talk about on this slide is that the way that this reaction is thought to work on this kind of material, for example, is that the bulk oxide is what's doing the conversion of water to oxygen, but the nickel oxide is actually a good material and has its band energies appropriately placed so that you can take the protons to hydrogen using the electrons. Okay, and a key issue here when you use these kinds of mixtures where you might have different surface phases doing different ones of the reaction, different parts of the reaction, are the relative positions of the bands. right? And so you always need to have a relatively good driving force for electron or hole transport to the surface to react with the species that are coming in for reaction. Right? And if you don't have that, even if the individual bands are well placed, then you can't get reaction. So for example, this shows, and actually it looks like I took a diagram for a different material, but this is the same idea. Right? That if you have a bulk material that has this conduction band, this is the bottom of the conduction band, and here's again the reaction that we want to do. That your surface material needs to have its bottom of the conduction band lower in energy so that there will be a driving force for electrons to go there, to want to form a photocurrent to go to the surface and react. Because if there's not that driving force, then they'll just migrate around inside the bulk material until they recombine with the hole, and then you lose the effectiveness of that incident photon that generated the proton-electron, or the hole-electron pair. Okay, and so this is an example of a related but different material that was found to be less effective because the band positions are roughly equal. And so you're going to tend to get a lot more electron-hole recombination because you don't have a driving force to the surface to do your reaction. And then, of course, you still need this driving force and this driving force to do each of your reactions that you need for the total water splitting reaction. Okay, so there are other schemes that are often used, and especially, so a lot of these materials, so these are pretty wide band gaps and would require ultraviolet light. They're not ideally placed for using the visible light portion of the solar spectrum. Right, and so what you typically want is something with with smaller band gaps in order to use visible light. And it can be hard to find something that has both a small enough band gap to be in the visible light region of the solar spectrum and that straddles the reaction of protons to make hydrogen and the reaction of water to make oxygen. Right, so that's a pretty demanding constraint. Right, and so what is being explored a lot for use instead is to have basically two kinds of catalyst particles that are floating around in your bath of water that you're shining light on. Right, and one of those particles is utilizing the holes, right, and reacting with water to make oxygen. Right, and then the electron that's created from the photoexcitation process then reacts with some intermediate species, some oxidant reductant that you're cycling through that is basically acting like sort of a co-catalyst here, that there's no net production or consumption of, but it's just acting as like an electron shuttle, an electron hole shuttle between the catalyst particles. And so this compound, whatever it is, will pick up the electron through a reaction and then carry it over here and react with this co-catalyst to release the electron, or to combine with this hole, that's being produced here in order to be oxidized and then continue this cycle. Right, so this hole that it reacts with has been produced through a second photon that's hit this other co-catalyst to generate an electron that's of higher energy than would have been available from this material that can react with with your protons to make hydrogen. Okay, so there are ways to try to use different oxidation reduction reactions that are kind of at an intermediate, they're in between the potentials of the proton reaction and the O2 reaction in order to get an appropriate driving force and with not too large of a band gap so that you can use visible light to do the excitation. And there are a lot of more complicated schemes than this to try to do that. But this is actually a pretty popular one right now. So any questions about how this works or why you use this strategy? Okay, so the final thing that I wanted to talk about over the next couple of minutes is in addition to doing water splitting, so you still have to do water splitting when you try to reform CO2, trying to take carbon dioxide from the atmosphere, so to do a complete reverse of the current utilization of fossil fuels. So of course when we burn gasoline in our engine, it produces CO2 and water, and now what we want to try to do is do the reverse of that with sunlight, providing the energy in order to take CO2 and water and make gasoline potentially, so try to make hydrocarbon fuels. Right, and this sounds like a difficult problem, and it certainly is. And there are different schemes, again, many different schemes that people are using to try to do this. Right? One of them that is probably the most commonly seen is that all of the photocatalytic activity is occurring for the water splitting reaction. And so you have a photocatalyst that makes O2 and protons. And again, just like in a fuel cell, you have a membrane that conducts protons, but not that is electrically insulating. And so the electrons that you generate come through this wire, basically, and recombine with the protons and CO2 to produce a variety of products. So one thing that you can produce is carbon monoxide in an undesirable reaction. On a lot of materials, you produce a lot of formate, which is definitely not what you want to produce. And then you also, on some catalyst materials, you can produce hydrocarbons, as we'll see in just a minute. Okay, another design would actually be to have a fully integrated photoelectrochemical device. So you have a single or sometimes stacks of semiconductor materials where you generate a whole electron pair. The holes go to do the to split the water and make O2. The protons go through channels in this electrode in order to react with CO2 to produce methanol or hydrocarbons or carbon monoxide, as we'll show in just a minute. Okay, and so with CO2, there are actually a number of reactions that you can do that are all at approximately the same equilibrium potential. Right? So they're all energetically relatively equivalent with each other. So you'll tend to be able to maybe have problems in getting selectivity toward a particular reaction, and that's where designing an appropriate catalyst comes in, to try to choose active sites that promote the rate of a particular reaction, since there's not a strong energetic favoring of any one reaction. Okay, one thing that you can always do when you have protons and electrons coming to a surface to react, especially a metal surface, is make hydrogen, okay, which is what you're doing in a standard water splitting photoelectrochemical device, and that certainly can still happen. All right, the protons and electrons can also combine with CO2 to make water and carbon monoxide, right, and this might be a desirable product, as we'll talk about in just a minute. They can also combine 8 electrons and 8 protons can combine with CO2 to make methane. All right, so starting to get into making natural gas basically from CO2, which is a fairly valuable product, although not nearly as valuable as trying to make gasoline. And then maybe most promising, over certain catalysts, you can make a significant amount of ethylene. Right, and ethylene is a nice molecule to make because since you have 2 carbon units and a carbon-carbon double bond, that gives you a functional handle that you can use to do polymerization, so that you can make longer hydrocarbon chains. So ethylene is a very promising product to make. And you actually, I'm not showing it here, but in the direct electrochemical reaction where you're adding lots of protons and electrons, you can actually get formation of 3 carbon and higher chains directly out of the photoelectrochemical process. Okay, so far the yields of those have been low, and so that's a big direction of research, is trying to find a catalyst that directly can make hydrocarbons from CO2, and really the longer the better. It would be great to have a directly usable fuel stream coming straight out of the electrochemical cell. Okay, maybe I'll back up here. So one reaction, we'll maybe focus on one of these reactions. And one of the reasons to focus on this is that this is clearly, based on a number of studies, the first reaction that happens even when you make the longer chain hydrocarbons, C3 and above. So the first thing that happens, logically, is that you take carbon dioxide and convert it to carbon monoxide. So you pull off one of the oxygens. Right, and this happens very effectively, in particular, over copper catalysts. So that's a metal we haven't talked about as much, but it seems to work very well over when you have copper as being the active material in the electrode. Okay, and this might be desirable, even stopping at carbon monoxide, right? Because if you remember from our discussion of biomass gasification yesterday, if you have carbon monoxide, and you also allow some of this reaction to occur so that you produce hydrogen, then you can make synthesis gas. So synthesis gas is just composed of carbon monoxide and hydrogen. And if we have synthesis gas, then I showed a slide yesterday, I probably should have copied it for today, where you feed synthesis gas into a variety of processes where you can make methanol, for example, using a very conventional petrochemical process. You can take it to phenyl compounds that are components of gasoline through the methanol to gasoline process. You can do Fischer-Tropsch chemistry over iron catalysts where you polymerize carbon monoxide in order to make diesel fuel, for example. And so synthesis gas can be a valuable stream in itself that can be integrated into existing petroleum refineries, if you can even just do this first reaction that's required for all the others. Although ultimately, from an efficiency standpoint, it would be better to directly produce longer hydrocarbon chains. Okay, one of the interesting things about the fact that copper is the most promising electrocatalyst, and I think this may be my last slide, so, is that copper is actually the catalyst that's used industrially for the water-gas shift reaction. So taking CO and water and making CO2 and hydrogen. And remember what we're doing here is we're taking CO2 and not hydrogen, but protons, and making CO and water. So just doing the reverse reaction is what we want to do in this electrocatalytic cell. Right? And it turns out that even though this is a very, as you might imagine, it looks like a pretty simple reaction, and it's a very much studied reaction, the mechanism for how this works, which we won't go through the details of, over copper catalysts was just figured out in the last couple of years. All right, so this is still very much an area of research and trying to understand how this chemistry really works for going in this direction or in this direction. And of course, now that we're doing this in a photoelectrochemical cell, right, instead of hydrogen, as is shown on the previous slide, what we actually have is protons. And as we've already talked about, having solvated protons is a lot different from doing a gas phase reaction with hydrogen. All right, and so there's a lot of study that needs to be done to determine how these pathways occur on the surface when you have protons. But at least there's a lot of promise that there are strong connections between a very traditional technique or a very traditional reaction that you would find in a petroleum refinery, the water-gas shift reaction or the reverse water-gas shift reaction, and this very new technology of using photoelectrocatalysis to convert CO2 and water to hydrocarbon fuels, or to synthesis gas, which can make hydrocarbon fuels. And actually, this is my last slide. One of the real issues with CO2 is that it's not very soluble in water, and so the types of photoelectrochemical cells that you would need to use would maybe be a little bit different. You can't just have something floating around in a bath of just water, but you need something that has a high solubility for CO2, so that you can get CO2 to the electrode to do the reaction. Right, and so there are a lot of materials that are being proposed that is going to make the study of these kind of interfaces even more complex. So I think I took this from an ionic liquids paper, so ionic liquids are kind of, as the name implies, pairs of ions that still can freely move about as liquids can. And the fact that these are charged actually makes them very good for having Lewis acid-base interactions with carbon dioxide and therefore capturing it and potentially bringing it to the surface. So people are just starting to study how some of these kind of strange solvents interacting with surface reaction species might affect the way the CO2 reduction rate, or the CO2 reduction to fuels reaction would occur. Okay, so I'll just put up this slide as sort of a summary of everything that we've tried to talk about, and hopefully have shown you some of the connections between the different techniques that, for example, electrocatalysis and fuel cells, we're just trying to do the reverse thing of what we're trying to do in photoelectrochemical cells for water splitting, that a lot of these reactions for water splitting and CO2 reduction to fuels are just reverse processes for what we're doing when we're taking petroleum to gasoline, so water gas shift versus reverse water gas shift, for example. And that a lot of the refining technologies that you would use, for example, for biomass, so taking the synthesis gas that you get from biomass gasification to fuels, you can generate potentially that same synthesis gas from CO2 and water in a photoelectrochemical cell. But there are actually, I think, a lot of connections in the technologies that can be used in catalysts for these different areas. But thanks a lot for listening. I know this is a very different talk from a lot of the others that you'll see during this, so you can maybe breathe a sigh of relief that it's over, but I'll be happy to take any questions now or after or during the break. So, thanks.
Okay, questions? So I have a question, and I apologise if you may have covered this in one of your earlier talks, which I wasn't at, but we all know that nanoparticles are more reactive than, larger particles, and I mean, obviously with these catalysis things, then the greater the surface area, then the greater the reactivity. But is there an extra factor associated with the increased reactivity of nanoparticles that could have an influence on some of the subjects you've discussed?
Yeah, so I guess it comes into play, and we did talk about this a little bit yesterday, so for example, nanoparticle platinum catalysts are actually worse for the oxygen reduction reaction in fuel cells compared to their larger platinum crystallite analogs, because on a per surface area basis, because they are more reactive, they have all these defects. And what you actually want, kind of surprisingly, for the oxygen reduction reaction is a less reactive particle than pure platinum, because these defects that you have on the nanoparticle strongly interact with the intermediates and just self-poison the surface. And so what you said is definitely accurate, that nanoparticles are almost universally more reactive. Sometimes that's the direction you want to go, is toward something that's going to form stronger bonds with adsorbates, and sometimes it's not the direction you want to go. And that actually gets around so there are also potentially interesting effects if you go down to really small sizes of these metals not really behaving like metals anymore, as you start to see really quantum effects. And that's a very complicated and controversial area that I didn't want to get into, because there's a lot of argument about what people are really seeing is, for example, a metal to non-metal transition as you decrease the nanoparticle size to a very small size. But there's a lot of debate around what kind of role that can play in catalysis. So everything I've talked about is on particles that you wouldn't consider to have really quantum confinement effects.
Right, but I mean, could the reactivity sort of do something with shifting these energy levels in a way that you could tailor?
Oh yes, that's certainly a good point, that you can affect the density of states at the surface, that you can affect the relative band position there, that can be important in having this kind of, when you generate the electron hole pair to keep them from recombining, you want all the way to the products a downhill energy landscape for the electrons, which is really the key aspect of the reaction. And so it could be that nanoscale features could play a role in making sure that it's downhill to the surface in terms of the band positions.
Sure. Okay, any other questions? In that case, Ivan, on behalf of the organisers, I'd like to thank Will for the 4 talks that he's given out here, and thank you for making the effort to come all the way out to Australia for this summer school,
Yeah.
So once again, let's just thank him very much for his presentation. And I believe it's morning tea time. We're going to reconvene at 10:30, and Ross McFedrin from the University of Sydney will be talking to you about metal materials. Okay, that's at 10:30. Right.
Thank you.